Imagine two supermassive black holes, each millions of times heavier than our sun, locked in a cosmic dance. They're spiraling closer and closer, destined for a cataclysmic collision that will shake the very fabric of space-time. But then, something strange happens. They get stuck. They orbit each other at a distance of about 3 light years, or 1 parsec, and just stop getting closer. This frustrating cosmic puzzle is what astronomers call the final parsec problem. It's a genuine head-scratcher, because, in theory, there's nothing left to slow them down. So, what's going on? Let's back up a bit. When two galaxies merge, and they do all the time, their central supermassive black holes sink toward the new galactic center. At first, they have plenty to interact with. They fling away surrounding stars and gas, losing orbital energy in the process and getting drawn closer together. It's like a celestial game of pinball, where the black holes are the flippers, and the stars are the balls. Each star they eject carries away a little bit of the black hole's momentum, causing them to spiral inward. This process works great for a while, but eventually, they clear out all the stars and gas in their immediate vicinity. They've essentially cleaned their room, and now there's nothing left to interact with. This is where the problem begins. Without any more stars to eject, the main mechanism for losing energy disappears. According to our classical understanding of gravity and dynamics, they should stall out, entering a stable orbit just 1 parsec apart, potentially for billions of years longer than the age of the universe itself. They become a binary system, trapped in a cosmic stalemate, never to merge. But here's the twist. We know they times do times merge. How? Because we've heard them. The incredible discovery of gravitational waves by LIGO and Virgo has opened a new window to the universe. These observatories have detected the ripples in space-time created by the violent mergers of black holes. We've seen the evidence. The final, powerful chirp of 2 black holes combining into one is a sound that has traveled across millions of light years to reach us. So, the universe is clearly solving the final parsec problem, even if our theories can't. The evidence is undeniable. The mergers happen. This means there must be some missing piece in our models, some physical process we haven't accounted for that gives these cosmic giants the final push they need to cross that last parsec. This discrepancy between theory and observation is what makes science so exciting. It tells us we're on the verge of a new discovery. For years, astronomers have proposed various solutions. Maybe there are still enough stars trickling into the core to keep the process going, just very, very slowly. Or perhaps the shape of the newly merged galaxy's core isn't perfectly spherical, and this asymmetry creates gravitational torques that help pull the black holes together. Another idea is that a massive disk of gas and dust forms around the binary, and the friction from this disk drags them closer. Each of these ideas has its merits, but none have definitively solved the problem for all scenarios. There's always some situation where the black holes should still get stuck. So we need something more fundamental, something darker. And this brings us to one of the most exciting and cutting-edge ideas in modern astrophysics, the dark matter solution. We know that about 85% of the matter in the universe is dark matter. It's the invisible scaffolding that holds galaxies and galaxy clusters together. We can't see it, but we can see its gravitational effects on everything we times can times see. The standard model of cosmology, called Lambda-CDM, treats dark matter as cold and collisionless. This means the particles don't interact with each other or with normal matter, except through gravity. They just swoosh past each other like ghosts. In this model, dark matter forms a smooth, massive halo around galaxies. While its gravity is essential for the large-scale structure, its ghost-like nature means it can't really help our stuck black holes. It doesn't provide any friction. But what if this standard picture isn't quite right? What if dark matter isn't completely collisionless? This is the core idea behind a fascinating alternative model called self-interacting dark matter, or SIDM. In the SIDM model, dark matter particles can actually bounce off of each other. They're not just ghosts passing in the night, they can collide, scatter, and exchange energy. It's a subtle change to the theory, but it has profound consequences. Imagine our 2 supermassive black holes orbiting within a dense core of this self-interacting dark matter. As the black holes plow through this sea of particles, the dark matter doesn't just move out of the way, the particles start crashing into each other. The black hole's immense gravity stirs up the dark matter halo, increasing the density and the rate of these self-interactions. This is the key. The interactions create a kind of effective friction. Think of it like trying to run through a swimming pool. The water provides resistance, slowing you down and taking your energy. In the same way, the stirred up, self-interacting dark matter creates a drag force on the black holes. This dark friction effectively saps the binary's orbital energy. The dark matter particles scatter off each other, carrying away momentum from the black holes, allowing them to sink closer and closer together. What's so elegant about this solution is that it kicks in at exactly the right time. The process becomes most efficient when the black holes are close enough to significantly stir the dark matter core, which happens to be at scales of, you guessed it, around a parsec. It's like a cosmic safety net that activates just when the traditional methods of losing energy fail. The self-interacting dark matter provides the final push, bridging the gap and driving the black holes all the way to their inevitable merger. This idea does more than just solve the final parsec problem. Models of self-interacting dark matter also seem to better explain certain observations about the density profiles of dwarf galaxies, which have been another long-standing puzzle in cosmology. So it's a theory that potentially kills two birds with one stone. Of course, this is still a developing area of research. We need more data to confirm if dark matter truly behaves this way. Upcoming gravitational wave observatories like LISA, the Laser Interferometer Space Antenna, will be crucial. LISA will be a giant observatory in space, capable of detecting the low-frequency gravitational waves emitted by supermassive black hole binaries times before times they merge. It will be able to listen to them as they spiral through that final parsec. By analyzing these signals, we can map out how quickly they're losing energy and determine what's causing it. If we see a pattern consistent with dark friction, it would be revolutionary evidence for the nature of dark matter. So, the next time you look up at the night sky, remember that it's filled with invisible mysteries. We have these colossal black holes locked in an epic dance that should get stuck, but somehow don't. The solution might lie not in the stars we see, but in the vast, invisible ocean of dark matter that surrounds them, a substance that might not be so ghostly after all. The universe is constantly challenging our understanding, and the final parsec problem is a perfect example of how a puzzle in one area of physics can lead to breakthroughs in another, connecting the largest objects in the cosmos with the smallest, most fundamental particles. Thanks for joining me on this cosmic journey. If you enjoyed unraveling this mystery, be sure to like, subscribe, and hit that notification bell so you don't miss our next deep dive into the universe. See you next time.